Hello, welcome to lip sync to the async in JavaScript, previously known as JavaScript Enjoys Our Tears. I'm Bob Fornal. I'm a senior solutions developer with Leading Edge in Columbus, Ohio. Somewhere back in the 80s or so, I got a computer science degree, learning some interesting languages like Ada back in the day. Progressed to teaching computers for the next 25 or so years. About 9 years ago, got an opportunity to step back into programming and remembered why I loved programming. And since then, I have been writing front-end code, working a lot with JavaScript. About 2 years ago, I did a deep dive into JavaScript, doing some heavy research, and realized I was seeing some pieces that would make an interesting talk, and that's where this talk came from. Okay, people say that JavaScript is an asynchronous language, that things occur at the same time, and I hear this argument all the time, but JavaScript really is, at its core, a synchronous, blocking, single-threaded language. Only one thing can happen at a time. Okay, and I say that, and if you've written JavaScript code, you've worked front end for a while, you've seen thread locking. Okay, you've seen something execute so fast and doing so much that nothing can occur. Your DOM doesn't update. You know, your browser kind of locks, and you have to shut everything down and bring it back up again. Some of these boundaries of the asynchronicity that we're going to take a look at, some of them are user interaction, network I/O, disk I/O, inter-process communication, timers. You know, so you're sending a request to the back end. You're kind of handing off control. You don't know what's going to happen. You don't know if it's going to error. You don't know if it's going to come back in a reasonable amount of time. You don't know if it's going to come back as one whole piece and in order. You know, all kinds of interesting things that happen there. Okay, so to start with, let's take a look at a couple of definitions. Parallelism, multi-threaded processing, scheduling, things occurring at the same time. Okay, this is not what JavaScript does. What JavaScript is, it's asynchronous. It's single-threaded, but it has an event loop, and we'll get into the event loop and what it does here in a bit. This is managed by cooperative concurrency. Higher-level tasks can occur at the same time frame. Code in the queue has some level of control over what's happening next in the queue. What we hope for is contention, multiple things that can occur within the same instant. Okay, so here in this talk, we're actually talking about JavaScript, okay? And to me, it was interesting to find out the set timeout is not a part of JavaScript. It's included in browser, it's included in Node.js, as is the event loop and the web APIs and the message queue and the task queue and many other things, okay? Interesting that the set timeout isn't, and we'll get into that later on. Okay, taking a look at the browser queue, okay, we have that event loop, we have a callback queue, we have the stack heap stuff that we deal with. There are web APIs, Ajax, DOM. This is a really simple image that I pulled somewhere off the web. It was just a quick Google search. There's hundreds of these out there. There are websites that actually show how this actually works. It's really kind of cool. But the really big one I want to talk about is where the event loop and the callback queue come into play. That single-threaded operation, when JavaScript has time, JavaScript being the single thread, it will go look at that callback queue and say, hey, what's the next thing that I could do now that I have some time to do something? If it's empty, it doesn't do anything. But if it's got a whole stack of stuff, it takes that first one, it executes it. When it's got more time, it executes the next one. Okay? It kind of makes things seem like they're firing asynchronously in some way if your code's not too horrible. Okay? I'm not saying your code's horrible. Callback hell. All right. In any talk of asynchronicity and talk of that control, we lead to callback hell, promise hell, the pyramid of doom, which is a symptom of problems. It's not necessarily the real issue. What we're talking about here is inversion of control. It's a trust point where the callback is passed. And we don't know what's going to happen once we pass that callback off. You know, does it crash out and have an error? Does it return in the right time frame. You know, we need to be able to reason about what's occurring on the other side, and it's very difficult to do. Coordination of data at higher levels to track across callbacks becomes complicated. Split callbacks are definitely difficult. Being able to separate out success and errors. Error first. Again, it's another trust issue, similar to what we have with those split callbacks with this success and error handling. And promise hell is really that flow control with bad styling. Okay, nested promises rather than vertical chaining. There have been big strides in getting rid of callback hell and promise hell and that kind of stuff. And we'll see some of that as we go through this slide deck. So I'm going to do a quick overview of what we're going to be covering here. We have a thought exercise. That's the very first thing we're going to do. And when we get to that code, this is really going to kind of set the format of what we're going to do. And this presentation should look a little unusual. If you look at the right side and you see my console hooping, we are going to be looking at a lot of code. And this is probably as close as I'll ever come to live coding. But this thought exercise is that place where we're going to show the code, we're going to think about it, we're going to talk through what might happen, and then we're going to execute the code and see what actually happens, and possibly, depending on the scenario, talk about why. Okay. We're also going to be looking at synchronous code, non-asynchronous code. We'll be looking at some really simple network code and a slightly more complex set of network code. API handling is what I'm talking there. And then ECMAScript 2015, we'll be looking at promises, both simple and complex. My list was too long to put it on one slide reliably, so continued here. We're looking at generators, in particular throttling. We'll be looking at user interaction code. We're going to be looking at event listeners, web workers. We'll be talking about timing code. Here we're talking about race conditions. We'll be talking about set timeout in much more detail than we have so far. And then we'll be looking at ES 2017, async await, a much cleaner way of doing things. So I mentioned the thought exercise, and here it is. I'm going to show the code. Okay, so on the right side, we're going to see the code. And typically, I'm going to start by showing what variables are up at the top. So in this case, we have the underscore time, which is a definition of how much time we want this to run, which is 10,000 milliseconds, 10 seconds. Okay, in the start down at the bottom, we're grabbing an element ID, the thought button. We're removing the hide class from it, and we're adding an event listener which fires event. Okay, the button is on the screen. We'll be adding to that. So that event is the event function up above, where it's going to execute the change color, change layout, and wait. So if we look at change color, it's going to change the background to red. If we look at the change layout, we're going to create an object, add the inner text thought exercise, and append that to the wrapper. And then wait has a simple while loop that's going to execute for an amount of time, which is at 10,000 milliseconds. So I'm going to execute my code here in a second, but what I want to do first, and this is how the thought exercise works, what do you think is going to happen? Okay. Now, normally I'm giving this presentation in front of a crowd, and I get lots of responses. So what I'll do is I'll talk through what typical responses I get, and then we'll execute the code. And typically I'll get about half the crowd will say, we're going to see everything turn red with the thought exercise. But there'll be the other half the crowd that's going to point out that, we got this loop in there. We don't know quite what that's going to do. So it might delay things. And I want to point out that I have this little icon up here that's on all my screens, and it's just kind of a remnant, but it's really good for this slide. I left it in for this purpose. Okay, so let's start this code up. Nothing happens till I click the button other than the button shows up. But notice it's highlighting up here. That's still interactive. Okay, I'm going to click the click me. Okay, drinking the Kool-Aid, and there we go. It's locked. Okay, so what's happening is that two-line set of wait code is thread locking for 10 seconds. Oh, and then we get that bright red. Okay, hopefully my presentation is not given super early in the morning and I'm shocking people too much. That thread lock occurred. Okay, and this is the proof that JavaScript is single-threaded. Okay, the simplest proof I can give. And that 2 lines of code we'll see later on. This exercise kind of sets the definition for how we're going to see code through this presentation. So let's clean that up. And let's move on to the next topic, which is non-asynchronous code. And we do have a debug piece we're going to show on this code. Let me show the initial code. There we go. down at the bottom, and that's before the start, or that'll be the third piece we show, okay? Let's take a look at the start. So here we're looking at non-asynchronous, okay? We can run this both asynchronously and non-asynchronous, and we'll do the non-async first. We'll execute the async, and then we'll look at the debug, okay? So we have this run sync that we want to look at, which is 2 up there from start, and it's console logging the start. It's firing a for each, passing in for each sync, and it's passing in a function which console logs the number times 2, fires the end. We do have this numbers at the top, which is an array of 1, 2, 3, and the for each sync executes a for loop and fires the callback, passing in item, which would be again 1, 2, 3. So I ask here, what do you think is going to happen? Typical answers are like, we're going to have the start 2, 4, 6, the end. We're going to have the start, the end, 2, 4, 6. And I see all other variations in there, but we're going to execute the code and see what happens. And here, okay, pretty simple example. It's going to execute the start, 2, 4, 6, the end. This is a synchronous run. Okay, things happen in order. Where it gets interesting, I'm going to reset the code here, is if you follow the asynchronous loop, or asynchronous function, the run async is firing off the for each async. So far that looks exactly the same as the run sync. If you look at the for each async, we've now wrapped the callback call in a set timeout of 0 milliseconds. Now this is where it gets interesting. It's 0 milliseconds. What do we think is going to happen? Again, we're going to get all kinds of answers ranging from the start, the end, 2, 4, 6 to the start, 2, 4, 6, the end, like we saw in the synchronous version. So let's run it and see what we get. We get the start, the end, and then 2, 4, 6. Okay. Our set timeout has an interesting trait to it, and I did track it down at one point in time, and I might be able to track down the link if somebody begged me to grab it. In the standards, there's a definition that there should be a default value, a minimum value. It's never setting set timeout to 0. Typically it's 4. I've seen a couple of older browsers that set it to 10. And we'll see later on that this is true, okay? I have some code that will actually prove that out for us. Now, my third example of this code, third piece of code is this debugger, okay? And the debug in and of itself is not the interesting part. It's that run async. So I'm going to execute the debug here. And it's got brought us in here and it's pausing. What I want to look at is this call stack down here. It's going to change as we step through. But one of the interesting parts, I'm going to be clicking this and looking for a particular piece, but we'll talk as we go. One of the interesting pieces is that when I was putting this slide deck together, I was finding a ton of documentation that was telling me to see the asynchronous activity occurring and those pieces occurring, you had to find this particular checkbox in the sources as you're executing through, and check it so that it would show it. And now if you see the set timeout async down here, it means some synchronous activities occurring. And if we come back up to where we stopped, it's right inside that set timeout. Okay, interesting that it's telling us that. There's no setting you have to turn on in your browser anymore. It's baked in at this point. Okay, so I just kind of want to point that out, that we have significantly better tools for handling that async debugging than we had previously. Now, simple network, I'm going to show the code here. And again, I'm going back to the set timeout. And the reason I call this simple networking, the set timeout really is one of those APIs that the browser has that we're going to work against, okay? In this case, it's a really simple, really is a simple example. We have a start, the end, we have a network request. We have a set timeout that's running for 10 milliseconds, or 10 seconds, 10,000 milliseconds. We should expect the start to the end, and then the console log with the async code 10 seconds later. Okay, so let's start it up and see what happens. And this is the point in every talk where I wish I had set that to more like 3 seconds instead of 10 seconds, because I have to burn a lot of time waiting for this to, hey, look at that pop up the async code after 10 seconds, okay? This sets us up for the next example. And in this next example, we're taking a look at complex network code, okay? In this case, I've set the time to 0 milliseconds. In the start, we're firing first. In first, we're firing a set timeout at 0 milliseconds. with wrapped in console logs. Console log 2 and 4. We had 1 and 5 in the first one. And then we're finding another one that has 3. And here I ask people, I don't go into much detail on how this all fires. What do you expect to see? 1, 2, 3, 4, 5? And some people say, no, we're going to see some other odd ordering of that. And they're right. So I fired this off. We do see the 1, 5 first, because that was in the start. Then you see the 2, 4 fire, because guess what? That set timeout, that callback function got put onto the event, put it into the queue on the event loop. And when JavaScript had time, it went and got it after it finished firing these 2 console logs. It went and grabbed it and it fired it. That second function didn't fire until it pulled that off that queue and then fired it, which is where we get the 3 at the end. Okay, a little more complex. And now we're going to step into something a little more modern, which is simple promise code. Okay, so here, promises helped us overcome that completion of this asynchronous activity. It also helped us overcome error events and handling that inversion of control issue where we give it away. Promises give us a trust that they only resolve one time, that they're either a success or an error, that messages that are passed are kept, that exceptions become errors, and that they're immutable once they're resolved. These are pretty significant things, given the fact that prior to that, we were using callbacks to handle most asynchronicity. Some of the issues of timeouts and promises are passing the values, the nested syntax, and occasionally handling error does some things, okay? So looking at the code here, we've got a start and an end. We've got the timeout firing up at the top there, which we've seen before. So we should expect that that's going to be after the end at some point. But we have that promise in there that fires and should resolve. And I get everything from the promise should be between the start and the end. The promise should be after the end, but before the timeout. The promise should be after the timeout because that's where it's placed in the code. And so let's execute it and see which one of those we get. Okay. Interesting. We got the start and the end. Then it fired the promise code. Okay, which kind of leads me to suspect, and I would bet if I looked in the specs, that the promises are part of JavaScript. They're running in the JavaScript code, unlike the set timeout, which is an API external to JavaScript that the JavaScript has to go to and come back to. But because the promise fired before the console log, something interesting is happening in there to allow the system to know that it can kind of delay that for a bit. It can delay that execution and hand off control for a short period of time. Okay, and not allow the thread locking that we would normally see to occur. So now let's step that complexity up and look at something a little more promising. Bad key of phrase there. Got the set timeout, but notice we also have a promise 1 and a promise 2. And if we look at promise 1, it looks the same as what we had before, only the number 1 thrown in there. But the promise 2 inside the then fires the promise 3. Okay. So again, we'll see variants from the start, the end, promise 1, promise 2, promise 3, timeout. We'll see the start, the end, and maybe the timeouts in the middle between the promises somewhere along the way. Okay, so let's execute it and see what happens. And we did get the start and the end, resolved 1, 2, 3, and then the set timeout fire. Okay, I've extended this example far enough in the past to prove it out. I mean, it doesn't matter how many promises I put in there. The JavaScript is still thread locked, although not for long periods, but it's thread locked long enough that that set timeout does not fire until after all the promises resolve. Okay, I've put in upwards of 1,000 of them just to ensure that what was happening, what I thought was happening was with JavaScript, okay? Now, the next example I want to look at here is generators. And when I got to generators, this was part of my deep dive. And when I got to generators, I wanted to find some practical examples. I kept finding these hello world type, really simple, completely impractical in day-to-day use. Didn't give me any reason to even think about using generator on a day-to-day basis. So I was looking for something. And I found this throttle. That was one that I thought was a really good example for this particular exercise. I did find another couple uses, and actually this slide deck is built on a generator. The actual deck itself is a generator. And the font size is actually a generator, allowing me to raise the font size up and down dynamically for the presentation. But let's take a look at this throttle. In the start, we're setting up the throttle. Okay, those 2 lines of code essentially set it up. You have to fire the throttle the first time before it does anything, which is what that THR next is doing. I'm passing throttle console log in 3000. Now, if you look inside throttle, we have some code in there that's setting up that throttle, that's setting a timeout. Okay, and the timeout is the amount of time passed in, 3 seconds. Okay, so let's start this code to see what happens. All right, so we started the code, nothing exciting happens until I actually fire a THR next with some string in it. In this case, I'm using send this comment like you see on the deck. And so I'm going to fire this repeatedly, and just keep firing it repeatedly a whole bunch of times. All right, and then we're going to wait a couple of seconds, and we should see send a comment. Now the interesting part is I didn't see the send a comment 31 times. I saw the send a comment 1 time. And it works over and over again. Once it's reset all the way out, it's ready to go again and throttle that again. Now, there are better ways to do a throttle, okay? And there are other frameworks out there that handle throttling differently and more cleanly than you see here. But the idea is that we have this pattern in place to allow, rather than cooperative concurrency, what's called preemptive concurrency, okay? With the generator being a syntactic form of a state machine, we can now reason about what's going on a little better. Okay, it allows for a non-run to completion behavior. Okay, it doesn't have to complete. It can go partway through and just stop. Okay. All right. So let's now move on to user interaction. Okay, and I'm going to show the code here, but there is no start here because this code is already executing on the objects. Okay, and what it's going to allow us to do is see the functionality of a drag start, drag over, and drop occur. Okay, and what you're going to see if you look at the console logs in these, we'll look at the drag start. We're going to see drag start in the event console. On the drag over, we're going to see a console log of the XY. On the drop, we're going to see console log of the drop and then the ID that was put in, that was added to the event on the drag start. Okay, so we're going to drag this and notice things are firing and it's, you know, just keep firing and nothing's locking up on us, which is really cool. We saw the drag drop down there bottom. If we scroll back way back up to the top, I'm going to have to keep going. There we go, all the way back to the top. We see the drag start. Okay. That functionality is still a part of JavaScript, but what we need to look at is, you know, how is that asynchronous synchronicity handled? And for that, you know, one of the pieces I want to look at is event listeners, which is a piece of what we're dealing with there. So in this case, I have essentially an anchor tag sitting out there that this code is connected to. So when we start, we're grabbing the ID of that link, and I'm only using that link as a holder at this point for this code. Okay, we're setting up the listeners, we're triggering the listeners. Okay, and then on the setup of the listeners, if you look up there, we're adding 2 event listeners, and we're passing it this output, binding a string. If we look at output, it's just a console log. Okay, and then the trigger does a set timeout for a period of time, and I didn't actually display the amount of time there, but I think it's a 0 millisecond delay, just enough to give it some time to have the DOM updated. And then you get a console log start and end, and your click handlers. So then here, what I'm asking is, what do you think is going to happen? You know, if this is asynchronous, you'll have the start and the end, click handler 1, click handler 2. If this is synchronous, we'll see the start, click handler 1, click handler 2, and the end. So let's execute this code and see what happens. And look at that. It tells me that the event listeners are synchronous, not asynchronous. It was an interesting fact to find out. So a lot of that's occurring with the DOM when you're dragging and dropping an element is synchronous on the JavaScript side, but realize that the DOM is its own separate API. Okay, it's got its own thread that normally we don't bind up too badly. It is slow, but we don't really bind it up too badly. So now let's change gears. Let's take a look at web workers. Okay, I'm going to start with the code that we have up here, which is the inline, the synchronous version. Okay, and if you look at the start, we can start at async or sync, but here we're showing just the sync just because there's so much code. So if we look at run sync, we're grabbing the progress bar, the percentage bar, and then we're executing crunch numbers inline, and we're displaying the percentile inline. Okay, the display percent inline function console logs and sets the value on the bar. Okay, and then the crunch numbers inline function is actually a for loop that's executing the callback, which is that display. But notice the next two lines. That's the thread locking code that we saw previously. Okay, on our first example. So it's going to thread lock for 1 second, right after it updates. Okay, if you've been developing it all on the front end, to the point where you've had to do something like this, you probably know that this is a pretty painful point to try and get it to not thread lock on you. So let's run this synchronous code and see what happens. Okay, notice our bar is not moving. Okay, it is incrementing the number. Okay, and I want to kind of stop right here real quick and point out that console log is not an internal part of JavaScript. Console log is an API. Okay, part of the browser. And it took this example for me to realize that. For years, I think I knew it somewhere in the back of my head, but it had never formally been stated. Okay, so now let's look at the asynchronous code. Now notice at the very top, we have a worker. And I'm going to show you the worker code here in a few seconds. We have worker progress. We'll see what happens there. We're going to see crunch numbers. We have at the start, it runs the async, and in the async, we're grabbing the element. We're posting a message to start for the web worker to actually start looping through and passing messages. And then we tell it what to do on message, which is the display percent, which is very similar to our display we saw previously, except we have to deal with that message and the message.data. Okay, so let's take a quick look at crunch numbers in our sources here. And I think I had it open. There we go. And it's really a simple function that executes a for loop. And it posts a message. And hey, look at that. There's that thread locking code all over again. Not a really complicated set of code to be executed, okay? But as we start this up, you'll see it's a pretty significant difference in functionality. The web worker has its own thread, okay, which allows it to be thread locked, while our JavaScript thread is not thread locked. Okay. Now, I get the question often on this one: how many of these can I run? Because I can do some heavy number crunching. I could do some really cool things, and the answer there is simple. It's a complex answer. It's a complex answer because each browser is a little different. Some have a fixed number, some do not. The optimal that I found has been around 20, but a lot of that varies on browser and how much memory and how much storage space you have and things like that. But once you get above about 20, your machine starts to bog a little bit. But 20 is really not too bad for some moderate type crunching. Okay. Now, comparatively, this next example is a little boring compared to the last one. Okay, this code is already executed. Okay, this is a race condition timing code set. Okay, so load timing was actually loaded in my index file in the header, and that load sync executed. All right, which attempted to get the get element by ID. Now, where the race condition occurred is the DOM hadn't updated, so it had nothing to grab. And thankfully, JavaScript is really nice to silently fail on that. And it didn't have the element. It bombed out on us. Okay? Whereas the load asynchronous in the same file, wrapped in a timeout, 10-second delay, did exactly the same thing. But if you notice out there, we have changed content correctly. That's the second timing element. Okay? And I will point out, one of the interesting facts is this is a race condition. It's a race to an end. Now, what's going to occur first? In the thousands of times I've run this and developing this presentation, putting it together and tweaking it and fine-tuning it and adjusting it and rebuilding it a number of times. So far, this has only failed to work correctly one time. And wouldn't you bet that occurred during a presentation? It did. Out of the 12 times I've given this presentation, not counting this one, it has failed in one presentation, not in the other 2,000 or 3,000 times I've done in development. Okay, it is a race condition. So now let's take a deeper look at the set timeout timer. And what I've done here essentially is written some code that on start will loop through 1,000 times, setting the time for whatever delay time we give it at the beginning. Okay, so we're going to try this twice. Once with a 0 millisecond delay and once with a 10. Okay, I'm going to do the 0 just to give you an idea of what that default is. Like I had initially said, it was about 4 milliseconds. So we'll see if that's what that is for my machine here today. Okay, and as I start that up, I would want to caution you that as you step up the amount of delay, as you step up the total repetitions, if you borrow this code from me, be very careful because this one will thread lock your machine very fast. We see here the request delay of 0. I'm going to start the 10 while I talk about that. The actual average delay is 4.81 milliseconds. It does not return at exactly 4, even though the default sets it to 4. Okay, it executes it when JavaScript gets to it. It could be 4, it could be 5, it could be 6. And as we look at the 10 millisecond, we see about the same amount of delay past the delay time we specified. Okay, at 10.74. Okay. So it's an interesting piece of code to kind of give us an idea of how the set timeout actually works, and to prove that that 4 millisecond delay minimum is in there, which explains a lot with those 0 milliseconds we saw up above in previous examples. All right, so for our last example here, let's take a look at async await. Okay, so I'm going to go through the code, then I'm going to go back again real quick. I want you to take a look and answer a simple question for me, just to yourself, okay? And here we're setting up a resolve state, whether it's going to pass or it's going to fail. I'm going to run this both ways. We have a start and we have an end like we've seen before. We're going to execute async await. If you look at async await, we have a try catch with a console log. If there's an error, we console log that. Okay, the console log, if you look in there, fires the async process. Okay, async process has a promise that can resolve either true or false. Okay, it can resolve or reject. Okay, and we're going to tell it which way to do it, and there's a 2-second delay. So what we should see, I'm going to be pretty straightforward with this. We should see start, the end, and then 2 seconds later whether it passed or failed. Okay, so let's start the resolve, and we're going to give it a couple of seconds. Look at that, it resolved out correctly, and that's exactly what we expected to see. We've seen enough examples to get a good guess. And if we click on the fail, we should see exactly the same functionality on the failure side. Okay. But the other piece I want to point out, now that I've executed the code, now that we've gone through the code, okay, your async await function that we fired there within the start had the async await code available to it. Okay, whereas we have the promise chain in the async process up above. Looking at those sets of code from a readability perspective, which one's easier to read? I mean, it's pretty clear that the async await makes our code much easier to read and reason about. And it really, at its simplest form, is a wrapper around the promise chain. Okay, it allows for very clean, easy, logical code to be written. Okay, so having gotten through all that, let's walk through a summary here, and then at the end of the presentation, I'm going to open up about probably about 15 minutes of question and answer at the end. Okay, so we've taken a look at both synchronous and asynchronous code using callbacks. We actually took a look at the debug and how the asynchronous activity is shown in our debugging of the code. We've looked at promise chains in various scenarios, both for legibility or lack thereof, depending on the case. But it was a significant step forward over callbacks. We've taken a look at generators. In particular, we looked at how to throttle with a generator. You've been seeing a generator, two generators actually, running my entire presentation. Okay. We saw user interaction and event listeners, which are synchronous, and how those browser APIs help make it look asynchronous. We've seen web workers, which are kind of cool to watch. I mean, that was an interesting way of processing that code. I don't know that that would be my production way of doing it, but it is an interesting exercise to look at having extra threads available. We looked at the race conditions that occur with load timing and why we have to load JavaScript at the end of our files, and in a lot of cases at the end of the body in your HTML. And then we looked at, as you still see the code here on the right, an example of async await and how the legibility has taken a major leap forward. Okay. We're going to wrap this up here. I appreciate everybody's time and coming out. I appreciate JavaScript and Friends for putting this talk on, for putting the entire conference on, for that matter. And I've been here, and you will be speaking with me live in the question and answer session that will start here real soon. Thank you.